Okay, so we're going to be graphing rational functions. We're going to start with the simplest of these, 1 over x, or this would be, it's called the parent function of rational functions because it's like every other function we're going to look at is basically just a modified version of this one. So, I mean, if you just plugged in these values of x, like if you plugged in -3, obviously that would be -1 over 3. -2 would be -1 over 2. I'm just going to move the negative sign to the top because usually it's usually if you have a negative on the bottom of a fraction, usually you can shift it to the top. -1 over 1 would just be -1. -1/2. Well, think about it. If you have 1 over -1/2, like well, just ignore the negative for right now, but how many times does a half go into 1? Well, that would be 2, so that's going to be -2. -1/3. If you think about that, that would be -3. Like how many times does 1/3 go into 1? Remember, if you divide by like a fraction between 0 and 1, your number actually gets bigger. So, but I mean, like I said, we're just plugging these in your calculator. 1 over 0, that's a problem. Remember, you can't divide by 0. So that's going to be undefined, or that's going to be a value in our range that we can't have. Like we're never going to have a y value that's 0. Also an x value, you can't have that 0. So there's nothing you can put in this function that's going to make it equal 0, and you can't put 0 in for x. So we're going to see we're going to have a little bit of restrictions when we graph this. And then similar idea, I mean, basically, if we plug in these positives, we're going to get the same thing, just not negative answers. So basically, it's symmetrical to what we just put above. This might not be super easy, especially if you're at home, but if we graph this, let's see what this looks like. So -3, -1/3. Zoom in. -3, -1/3 would maybe be about there. Oops, oh gosh, erase the whole thing. -2, -1/2 would just be slightly lower. -1, -1 would be here. We can't plug in 0. And then, so one thing we're actually, if you kind of remember, we're going to have some asymptotes. Basically, our function can't equal 0 for the y value and the x value. Like you can't plug in 0 for x, and your function can't, like there's nothing you can plug into that function that's going to give you 0 as well. Like, I mean, 1 over 1 is 1. 1 over whatever, you're going to get something that's not 0, positive or negative. So we're going to see when we graph this first part, like these first points, our graph's going to get really, really close to the x-axis as it goes to the left. And then as this part goes to the right, it's going to get really, really close to, oops, that's kind of weird how that just did that. It's going to get really, really close to your y-axis, but never touch and never cross. So I just graphed these first points here, and then we're going to graph our positive points. So like 1/3 and 3 would be approximately here. 1/2 and 2 would be approximately here. 1, 1 would be here. 2, 1/2 would be approximately here. 3 and 1/3 would be here. And if you could plug in more values, but basically you're going to see it's a similar idea. It's going to get really, really close to your y-axis as it goes to the left. And as it goes to the right, it's going to get really, really close to your x-axis, but never cross. Like it's going to get super close. So let me maybe draw that a little bit better. But it's just going to get like for example, if you did 1 over 1,000, it's going to be like so close to 0, but not ever going to make it there. So this is what our graph looks like. You're going to see when you graph rational functions, you get these two parts of your graph that are split. We call these our branches. So the graph of the parent function, 1 over x. Let me just make sure. Is this next spot? I'll make sure. And this graph is called a hyperbola. That's like the fancy or the proper, like kind of like when we graph a quadratic, we call it a parabola. When you graph a rational function, you're going to get something called a hyperbola. So that's what this shape of this graph is called, where you basically have these two split branches, which consist of two symmetrical parts. Like I said, these are called branches. Like we have a branch in the bottom left quadrant, and we have a branch in the top right quadrant. So there's two different parts, and we call these branches. Let me just make sure the domain should be all real numbers except 0. Our domain would be all real numbers except x can't equal 0. Like if you kind of see, like, remember our graph got really, really, really close to the x value that's 0, but never cross. And same idea with our range, it would be all real numbers except x can't equal 0 as well. Or sorry, not x, y, since we're talking about range. Y can't equal 0. And then a little bit, we mentioned these vaguely when we did a little bit with our exponential graphs. We didn't do as much as honestly maybe I should have this year, but an asymptote, you remember it's a line which the graph approaches or gets close to. But it's a line which your graph approaches, but never crosses or touches. And keep in mind when you're graphing these, like these dotted lines I put in my picture, like in blue, those aren't actually part of your graph, but they're helpful to draw on just because it helps you get the shape of your graph if you're graphing by hand. But if you graph this function in Desmos, you're just going to see what I have in red in my graph, just like the two branches. Like Desmos isn't going to graph your asymptotes because it's not actually part of the actual graph. Sorry, that's a little sloppy. It never crosses or touches. So that's what we're going to see when we're graphing these. We're going to get a shape like this. But one thing to keep in mind when you have rational functions, it's a lot of times you're going to have horizontal asymptotes and vertical asymptotes. So you can have both, like most of these problems we're going to see, you're going to have multiple asymptotes. Okay, so, but this is what a rational function looks like. So if you've ever wondered, like you graph like 1 over x or 1 over x plus 1 or 1 over 2x or 1 over, well, 1 over x squared actually might change things. I'd have to think about that. Well, maybe not. Here, well, I don't want to like throw it out there. Okay, so this is called our parent function because like I said, when we look at other rational functions, it's going to be similar to this, but shifted. It might be reflected. It might be translated left to right, up, down. It might be stretched or shrunk a little bit. But that's kind of what we're going to be looking at. So basically, we're going to look at a couple more examples of these, but a couple tips. You can see basically, depending on how you change this function, it can do different things. Like if you have a number added or subtracted in the bottom, it's gonna move your graph left or right. Oops. You have a number, sorry, for your K. If you have a number added on the outside, that's gonna move your graph up or down from what we just sketched. The A value is gonna determine if it reflects or if it shrinks and stuff. But honestly, you don't really need to memorize these rules too much, but if you remember when we talked about transformation rules, like it does apply. But really what we're interested in is our vertical asymptote is going to be at our H value. Basically, your vertical asymptote is always going to be what would make your bottom of your fraction equal 0. And then your horizontal asymptote is always going to be your K value. So looking at like this next example, y equals -3 over x. I always start with my horizontal and my vertical asymptotes personally. I mean, you can kind of do these a little bit out of order. But remember, our horizontal asymptotes are k value. So since there's nothing added or subtracted like outside our fraction, we're just going to have a horizontal asymptote. And your horizontal asymptote, that's going to be a line that that would be like, oh, sorry, it's going to be y. It's backwards. It'd be y equals 0. Like that would be a horizontal line, like basically the x-axis. Our vertical asymptote is going to be what would make the bottom of this fraction equal 0. I mean, it's just x, so that would also be x equals 0. So if you want, I'm going to go ahead and just sketch my asymptote. So it's the same as what we just did. Basically, it's never going to cross our x-axis and it's never going to cross our y-axis. Because this is, remember, this is x equals 0. This line would be y equals 0. If it, not that it really matters too much, but. Well, and since, well, if you kind of think about our picture, since it's never going to cross the x-axis or the y-axis based on our asymptotes, I mean, we're actually not going to have any of these. because it's not going to cross or touch either one of those axes. So if we graph this, you could just make a table of value if you want. So when you're making a table of values, I would look at your basically your axis that's cutting off your x value. So we want to go to the left of our vertical asymptote and to the right. So because x equals 0 is going to be undefined. So basically, I want to just plug a few points on both sides of that. So for example, maybe if I plug in like 1, 2, maybe 3 points on both sides. I bet 2 is fine. Let's see what 2 looks like. So if you plugged in 1, that would just be -3/1. That would be -3. If you plug in 2, that would be -3/2. Then maybe if we go on the other side, we'll plug in a couple points. If you did -3/-1, that would be +3. -3/-2 would be +3/2. So one tip is, it's kind of like when you graph quadratics, like as long as you pick the same like intervals on both sides, your values are going to be symmetric. So you can definitely save some time. But if we plot these points, I'll start with the negative x value. So -2 3/2 would be up here. So -2 3/2 would be roughly halfway between the 1 and the 2. -1 3 would be up here. And that's honestly, you could get more points if you want, but you can kind of sketch it in. It's going to make that branch. It's going to get really close to the y-axis, and it's going to get really close to the x-axis when it goes here. So 2 points is usually good. I mean, you can do more if you want. And then if we plot the other points, 1 -3 would be down here. 2 -3/2 would be about here. And same thing, it's going to get really close to the y-axis, get really close to the x-axis based on those asymptotes. So our domain, I mean, it's all real numbers except x can't equal 0. Our range would be all real numbers, but y can't equal 0 based on our asymptotes. Or if you just look at your graph once you got it sketched. And let's just look at one more problem. And then, like I said, I'll give you guys the last kind of chunk of class to work on your quiz, or if you got anything that's missing. And I need to update grades too. I know some of you guys did some Delta Math. I apologize. So like I said, I usually start with the horizontal asymptote and the vertical asymptote. So if you remember the horizontal, let's just start with the vertical asymptote. The vertical asymptote is basically what would make the bottom of your fraction equal 0. Like what would make it undefined? What can't you plug into this function? Well, you can't plug in +2, right? Because if you plug 2 in, you would get 0. So my vertical asymptote would be 2. And remember, it's backwards. It's going to be y equals, because y equals, oh wait, no, it's not. It's going to be x equals. What am I saying? It's going to be x equals 2, because that would be the vertical line. For our horizontal asymptote, if you remember, that's your k value. So what's added or subtracted outside our function, so that would be 5 in this example. So our horizontal asymptote is going to be y equals 5, like the k value. So I'm going to draw in our asymptote. So we're going to have a vertical asymptote at 2. Oops, what happened here? So our vertical asymptote's at 2. Oops. And our horizontal asymptote's at 5. Ooh, ooh. So when you make your XY table, here's my advice. You're gonna look at your vertical asymptote. So our vertical asymptote is at 2. So you always kind of want to put, like, it's kind of like when you put your vertex in the middle, you're going to kind of put your vertical asymptote in the middle. And then you're going to go 2 points on both sides, at least 2 points. Like I said, you can do as many as you want, but at least 2 points. Maybe I'll plug in 1 and 0, and then I'll plug 3 and 4. Sometimes you might want to pick different numbers if it looks like it's going to work out nicer. Like this one's probably not going to work out super clean. We'll see how it goes. But so for example, if I plug in 0, that would be 1 over -2 plus 5. That would really be negative. I don't know how good you guys are at mental math, but if you plug in 0, you would get 1 over -2 plus 5, that would be negative 4 point, or sorry, positive 4.5. If you plug in 1, you would get 1 over 1 minus 2 would be negative 1. So that would be negative 1 plus 5, that would be 4. And you're going to see it's symmetrical, but if you don't believe me, if you plugged in 3, that would be 1 over 3 minus 2 is 1 plus 5, that would be, oh, actually, it's not going to be symmetrical. I lied. Yeah, one thing, it's not going to be symmetrical if you have different asymptotes. So actually, you do need to be careful. That's only going to work when you have like 1 over x if you don't have these shifts like with your asymptotes. And then if you plugged in 4, it'd be 1 over 2. That would be 5.5. Let me just double check my math. Yep. So then if you graph these, I'm going to start with the like 0 and the 1 x values. If I plug in 0, 4.5, that's going to be up here, pretty close to the asymptote. 1, 4 is going to be here. So you can kind of see it's making that branch shape. Basically, it's just going to be like contained between those asymptotes, but get really close to both of them. If we graph the 3 and the 4 x values, 3, 6, it's going to be above this other asymptote. So you can, and then 4, 5.5 would be a little bit lower. But you're going to see basically it's contained between these asymptotes. And realistically, the point, I mean, honestly, the points are just kind of letting us see which, it's not really a quadrant, but like which sides of your asymptotes you're going to be. And one thing you should notice, you're always going to be opposite of each other. Like you could be here and here. Or if your graph like reflects, you could be like here and here. So like just keep in mind your branches are always going to be in like diagonal quadrants from each other, if that makes sense. Like you're never going to have like, at least I can't think of an, like, I'm sure maybe it's possible, but you should never have them like the top and bottom like right next to each other. So then we just want to answer some of these questions. It wasn't super neat. Well, we did get our y-intercept was actually this point here. That's actually the y-intercept. That's where it crosses the y-intercept. But the x-intercept, I really didn't get a good point. Like I didn't plug it in, but you can kind of see it crosses around there. If you actually want to get your x-intercept, that's where your y value equals 0. You could set 0 equal to this. Let me see what it is. So like just for purpose of time, I'm not really super worried, but that's how you would actually solve for your x-intercept. Let's see, what did I get when we did this? Oh, I didn't write it down when I did my key last year. Here, we'll do it. So it would be, if you're writing this, you don't have to write this down. I'm just going to do this quick. You can multiply the x minus 2 over. So you would get, you have to distribute. So you get negative 5x plus 10 equals 1. If you subtract that, you would get 9 over 5. So our x-intercept would be 9/5, 0. If you look in that from our graph, that's kind of what it looks like. It's between 1 and 2. So it should be positive because I got a negative over a negative. Unless I goofed up, but it makes sense too, just from the picture, it should be positive. And then our domain, well, it would be all real numbers, except, remember, domain is our x value. So the only x value can't be is 2. That's where our vertical asymptote is. Basically, your domain is going to be everything except your vertical asymptotes. Your range is going to be all your real numbers except your horizontal asymptote. So y can't equal 5. So if it's a helpful tip, like your horizontal asymptote goes with your range, the vertical asymptote tells you about your domain. And that's it for our notes.